in our unit on queuing theory. I'm going to pay attention for the next few minutes to an example in Blanchard and Fabrici's text. Section 10.2 covers the basics of Monte Carlo analysis, and it shows you an example. I'm going to use their example, but they don't really show you the calculations you would do if you wanted to write your own little Monte Carlo simulation. There are plenty of simulation tools you could build a Monte Carlo in. So if you've taken a simulation course or anything like it, operations research, you probably have your own simulation tools you could plug this into. But to keep it simple, I like to build very simple simulations in Excel. So that's what I'm going to use here is a basic Excel spreadsheet to do the job. So the way the example works in Fabrici, we have basically an arrival and a service time distribution for which we want to build a Monte Carlo simulation. So they give us a time of between arrivals of customers or processes in the flow with an expected value of 6 time periods. I'll probably say minutes several times, but in the text it's just 6 time periods going through. 6 1/3 roughly time periods between each arrival. That's an empirical distribution. And we're given a service time distribution to say the service time for each arrival has a mean value of 5 time periods or minutes and a standard deviation of 1. So if I look at these two distributions, I can see that the arrival time of every 6 1/3 minutes is longer than the average processing time of 5 minutes. But because of the distribution of those 5 minutes and the distribution of the empirical distribution, I'm probably going to have periods where I get arrivals faster than I'm expecting, or I do processing slower than I'm expecting. So even though the average service time is less than the average arrival time, meaning if I have a queue, it shouldn't get too big, because in general, things are arriving slower than I'm processing them. What I might need to know as an engineer is what is the risk that the system, in fact, will hit a bottleneck and potentially could go to a catastrophic failure at some point. So Monte Carlo simulation says, let's put these distributions together and run them through a series of repetitions, and let's see what the system does as it goes through. So the first thing I want to do is create a generator of the number of time periods between the arrivals. And I didn't pick 4 through 9 at random. Those are the time periods in the empirical distribution in the text. So we're told in the text the probability of each of those occurring. So 7.5% probability that the next customer will arrive after 4 minutes. A 20% probability that they'll arrive under 5 minutes within the next 5 minutes. So those are simply the probabilities we're given in the text. So I can make those cumulative probabilities to say there's a 27.5% probability that I'll have 4 or 5 minutes to the next arrival. So I've basically generated a range from the base. So 0 to 0.75 is going to be 4. And I stack those up. And you'll see in a minute why I do it that way, because I want to use an Excel lookup function to look up the numbers that are involved there. We'll come back to that in just a minute. I want to do the same thing for the service time distributions. I have a mean of 5 and a standard deviation of 1. So even 3 or 4 standard deviations above the mean would only be 9. So I'm going to run my n factor to numbers much larger than that. You're safe doing larger numbers, but you're at risk if you use smaller numbers. So for instance, if I go back to the PDF of the original distribution, I should have checked to make sure those in fact add up to 1, which they do. You want to make sure that the conversions you're doing for your distributions in fact add up to 1. So I want to make sure I can cover that in my normal distribution here as I put my data in. So for 0 to n possible service times, I'm going to plug in a normal distribution for that. And then for that, I'm just using a standard normal distribution curve with the standard and the standard deviation that I've got going on. So there's a very, very small probability that I will finish my servicing in 0 minutes. Still small probabilities of otherwise going through. So I've got a 50% probability of finishing in 5 minutes, which is my mean value. That's what I would expect. An 84% probability of finishing in 6 or less, things of that nature. So I've got my distributions here in terms of my cumulative probabilities associated with each of these that I'll do for my lookup. So here's basically my probability data for the amount of time between the arrivals of my customers and the amount of time it's going to take to serve their needs when they come in. So having done those distributions, then I'm ready to start plugging in my simulation. So I'm going to simulate a number of customers. I think I built the simulation to be 75 customers as I go through. Nice thing about Excel is you can copy the formulas all you want and generate as much data as you want as you go through. But I'm just going to simulate 75 customers to see where that takes me. So the first thing I need to know for each customer is how many minutes before they arrive. So how quickly do they arrive? I know the average is about a little over 6 minutes each, but I have to generate that as a random number. But I want it to be according to the distribution, the empirical distribution. So I have to be able to do that. To generate that, I'm going to need a distribution that I know is uniformly distributed. And I'm using the Excel random number function, which generates a random number with a uniform distribution between 0 and 1. I think in the text, they have you looking up the random numbers in an appendix. That's another way to do it. As long as you're using a uniformly distributed random number, the process works. And Excel is very, very nice because it can generate these random values for us. And then I'm going to use a lookup value. What I want to know is how many minutes in my distribution does that random number represent. So I'm going to plug in my values now. I ignore the first value because I assume the simulation starts when the first customer arrives. I don't need a number of minutes till that would really be a 0. I could have even plugged it in as a 0 if I had wanted to. So here I generate a 0.156 as my random number. I'm going to look up 0.156 here in this distribution. It's a lookup function. I look for the largest value in this list that isn't larger than my number. So 156 falls between the 0.075 and the 0.275. So really it's the 0.75 value that matters. So the second customer is known to arrive in 5 minutes. That's where this 5 comes from. So using a lookup function, if you're not used to the Excel lookup function, you should learn it because it's a very, very valuable thing to know. It says, in this case, take the probability that's in column I, the random number, look it up in column C. Okay, the lookup looks for the largest value smaller than the number I'm looking up. And then when you find it, take the value in column A that corresponds to it. So here's 1.858. When I do that lookup of 858, it falls between 8 and 9, so the value I want is an 8. Okay, so this 0.858 gives me 8. So I'm generating data in column J that matches the empirical distribution that I was given, and I'm doing it by a lookup that involves a uniformly distributed random number. And I can do this for any distribution that I want there. The service time now, I'm going to do the same thing again using this normal distribution as I go through. So let's see what that looks like. Again, I generated a separate random number for all 75 cases. You can't reuse the same random number because then you're confounding those two variables. Generate a separate random number for each value you're trying to generate and then perform the lookup to look up that value. So this 0.365 gives me a service time of 4. And sure enough, if I come to this service time distribution and look up 365, I find that it's larger than 158 but smaller than 0.5, so the number I want is 4, and that indeed is what the lookup gives me. So again, my service times are normally distributed with a mean of 5 and a standard deviation of 1, and I did that through a lookup using a uniformly distributed random number. So if you know a distribution and can build its cumulative probability and then generate a uniform dispersed random number, you can convert that uniform dispersed random number into a value that is aligned with the distribution that you started with. So now I have a number of period to arrival that fits the empirical distribution with an expected value of 6.325, and I have a service time per customer 4 to 9 minutes that fits the normal distribution function that I know for my service time. So that's my base data coming in, and now I can look at the actual simulation that works on that. You'll notice that when I'm manipulating this spreadsheet, you're not seeing the values change. That's because up here under calculation options, I have the calculation options set to be manual, which means when I update the spreadsheet, it doesn't update all these values. If you leave it on automatic, then every time you update a field, it refreshes all of the random values. That's okay, but you're going to be constantly seeing your data values change if you do that. So I set it to manual, that I manually hit the calculate sheet value anytime I want. So every time I push this calculate sheet button up at the top, it generates a whole new set of random numbers and gives me a whole new set of values going through. Like I said, if I had this set on automatic, that would happen every time I update a value. If I just type a character into that, everything I do gets a new value. So for simulation spreadsheets, you're probably going to want to set this to manual, or the sheets will drive you crazy. Just hit the calculate sheet whenever you want it. If you're in a particular hurry, the F9 key does the same thing. Okay. So now I know my periods to arrival. Let's continue the Monte Carlo simulation. The number of periods that have elapsed since I've got here. It's really just the running total of all of those we've generated so far. So the earliest time that the sixth customer can be processed is going to be after 30 periods, because there are 24 periods stacked up in the customers before. So assuming they come first served and that my process isn't falling behind, I'm going to be able to process them based on their arrival order coming into the cumulative probabilities. So that gives me the earliest possible start time for each one. So the seventh customer arriving here, the earliest they're going to be able to start is at time period 41, because I've used up all those time periods getting to this point. So for the moment, column K and column L are the same, and that's what I want so far, but that will change in a minute. I can also compare those two values to see how long a given customer might be waiting in the queue, which again is 0 for now because I'm not hitting any service time, but that value will change as I proceed. So now I can look at when is the service of the item going to be done as I go through. So this first item by definition started at time period 0, but it takes 3 time periods to be serviced, so it's going to be done at the end of time period 3. The second customer arrives at the end of time period 8. Okay, so therefore it can't start until the end of time period 8, okay, which means they're going to be done after seven time periods at time period 15. So even though there's not 15 time periods involved here, there's 10 time periods involved, but they tend to work their magic in terms of potentially holding things up. So I want to typically calculate, in addition to when they'll be done, how long they'll be idle. Because this first item was done at 3 minutes, but the second customer didn't arrive until 8. So there's actually 5 idle minutes in between that I might want to take into account. Do I want my process to be that idle? In essence, I've tuned these so close together that when a customer arrives quickly, I run the risk of having an idle process that's going to slightly to waste as I go through. So you should be calculating your idle periods coming through. And then you also want to know for any given item, how long was it in the system? Okay, so this first item is in the system for 5 units of time. It's the service time, gives them five in. But as I go through, so for instance, item 12 down here, okay, has an actual wait time, because the earliest they can start is in period 72, but they actually arrived in period 71. So they had to wait a period for the service process to catch up, and then there was 7 minutes of service time to get them done. So that process was actually in the system for 8 minutes, even though it only got processed for 7, because it had to wait. The 13th item is even worse case. It has to wait 3 minutes because it arrives at 76, but the prior item isn't done until 79, so it loses 3 time periods and then gets processed for 6. So it's actually in the system for 9 minutes, seeing its way through. So ideally, we want to analyze all of this as we go through. So for that, I bring some totals up to the top, and I've highlighted some of the important ones. Okay, the wait time has a max of 2 and a total of 8. So this entire system, while processing the 75 customers, had a total wait time of only 8 minutes. 341 minutes spent processing. So the system spent 98% of its time processing and 2% of its time waiting. And it did, in fact, have, on average, almost 2 minutes of idle time per customer. So if this is a very expensive process, I might want to work on that. I might want to reduce the idle time. But if it's not an expensive process and the goal is just to maximize throughput, a wait time of only 2% is not too bad. Things are flying through the system pretty well. On average, they're coming through the system every 4.6 minutes. That's not bad considering that it's a 5-minute average processing time. So the fact that the average time in system is less than the average processing time is a pretty good basic mean, even though the mean arrival time for these 75 customers turned out to be 6.4. So the statistics you see here will not exactly match the distribution, but it's an example of a real world run of your system for 75 customers. Like I said, I can hit calculate sheet and it's going to give me a new set of values coming through. If I can recalculate, here's a run where it's a little less time, but still almost 2% spent in my wait state as I'm going through. So here I'm seeing that the longest anything has to wait, I'm watching this max wait time value here as I recalculate. The longest, there's one where someone had to wait 3 units of time as they go through. Now only 1. So I'm looking at the maximum wait time to know how long something might have to wait while it's in the system. But as long as my processing time stays fairly high, I seem to have a pretty useful system going through here as I go. So my Monte Carlo simulation shows that even though my mean processing time is only slightly lower than my expected arrival time, it doesn't look like I'm going to hit a lot of bottlenecks when I build this system. That I'm going to get things through the system fairly quickly. I'm not going to rack up a lot of idle time where things can't be processed. I'm waiting for customers to arrive. My in-system process is not that much longer than the average service time, so my waits are not contributing very much. And my arrival times at 6.147 are pretty close to my expected value. So it looks like my system will run well for an extended period of time. And I can, by hitting calculate sheet, keep redoing that calculation to see what that number does. And as long as that column P statistic is very, very high, approaching 100%, I'm pretty happy. That's 4% there. 96.4 is the worst we've seen so far. There's a 95.5, but the numbers seem to average out pretty well. So it looks like up to 5% wait time might be the cost of bringing things through this system. Looks like a very efficient system. I would probably be safe moving forward with the design on the assumption, but again, not recognizing that it's not going to be a perfect system. There will be items that have to wait as they go through, and I can play with that. I can also use the Monte Carlo system to play with things a little bit. What happens to the data if it turns out instead of 5 minutes of processing time, that on average it takes, say, 7. Let's change this to a 7. Okay, and recalculate the spreadsheet and see what happens. And oh boy, that has a huge impact, because now I've got only half my process is productive, the other half is items waiting. Let's run it a few times to see if that's realistic. Here's a case where only a third is processing and 2/3 is waiting. That's not good. 3/4 waiting. 3/4 again. Here's a little more than half processing and a little under a half waiting. So if my estimate of 5 minutes for processing on average turns out to be wrong, and it's really 7, this system's going to be in trouble as I go through. It's racking up a lot of time. So you've got things arriving every 6 minutes, but on average they're waiting 7 minutes. So they're spending more time waiting than the arrival rate, which means you're looking at a significant queue coming through. And in fact, that can be misleading in terms of my data here, because I've got all kinds of items waiting as I go through. I'm out to 469 units, time periods, just to keep things processing, and I've got a potentially huge queue as everything here is waiting. So as you get worse and worse data, you might want to extend your simulation to run a lot more than 75, but in fact it wouldn't fix the problem here. The problem is that it takes longer to process something than the time required for the next one to come in. So you'll always be getting more into your system before you have processed them. And thanks to the distributions that are involved, you might catch up a little bit at times, but other times you're going to fall farther behind. But on average, you're going to keep falling farther and farther behind as you go through. For instance, if I change this to 9 minutes per unit and recalculate, that I end up spending 92% of my time. I'm starting to get into a log jam as I go through. What if it were 10 minutes coming through? Do that calculation. 94% of my time is spent in waiting. Some of the items are waiting 245 time periods just on this kind of a run. So it tells me, using Monte Carlo simulation, that I better be right about this number 5. It's really, really important. So running your Monte Carlo and varying the different properties will tell you a lot about the viability of your design. So this design looked like it was going to be a good, solid design if I could actually deliver on that 5-minute service time. But if I think I might potentially double it someday, either because the process degrades, the tools get old, my workers get tired, if I can't deliver the 5, if there's any chance at all that it's going to end up taking 10 minutes to provide that service, I better pause right away and rethink how I want to do this basic process, because it would not be working. As soon as I've got 6, 7, 8 minutes of service time per unit, the whole process starts to fall apart, and therefore the entire system that this process is part of starts to fall apart. And that's the power of Monte Carlo simulation. It takes distributions. This one started at 5. When it was a 5-minute service time and a 6-minute arrival time, it looked like everything ought to be fine, and in fact the simulation shows, if we recalculate it again, that we for the most part are. We're looking at under 5% waste associated with wait times as we go through. And the majority of these rows have a 0 in the wait time. A lot of them are not waiting at all. In fact, the worst case is a max of 2. There's an item in this list somewhere that had to wait 2 minutes to get processed as they go through. And there's only a wait time of 14 minutes total. So if we deliver on the 5 and if the 6.3 arrival rate is accurate, this process will work. So Monte Carlo is a good way to quickly validate through a quick simulation that you can build in a matter of minutes. Will my process really deliver on the need, and how sensitive is it to minor changes in the overall performance as we go through? So you can vary the basic key values to see what would happen as we go through. So that's a basic Monte Carlo simulation. You'll use it a lot in your basic process. It's not required that the distributions be empirical or normal. It could be any distributions. As long as you can convert the uniformly distributed random number into the distribution in question, you can build this kind of a simulation, and I urge you to.